buy one, we recommend the adapters made by Kramer.
Kramer, right.
Kramer. Those we found are most reliable.
Got it. Yes. Perfect. Perfect.
All right. Have a good class.
Yeah. Thank you. Take care. Can everyone hear me at the back? Yeah? Great. Does the microphone work? Yeah? Sorry?
Are you recording the lecture?
Yes.
Okay.
I'm recording both the Zoom and with that. Okay. So I don't know, and I'm kind of like trying this thing so we can see like maybe it's not needed to do both.
Okay.
What? Yeah.
I guess both is preferable.
Both is preferable. Yeah.
Let's see how which is better next time.
The audio. I checked. The audio works on Zoom, right?
Yeah.
I think you should. Yeah. We'll start in 1 minute. We'll give you a bit more time if anyone is coming also. Sorry? Yeah. I know. It's first day in class.
I bet you would be like me, it's like 6 a.m. in the morning. Fine. What a great start. I know, man.
How many of you are in CSE? Just to get an idea of, I see. Applied maths? Bioengineering, Any other departments? Electrical engineering, yeah. Sorry? CSE, nice.
They get to control the other side.
Mm-hmm. Okay, so we get started. Welcome to CSC 242 Machine Learning. So I'm Razvan Marinescu. I'll be teaching you machine learning this term. So a few words about myself before we start. So I've been working on machine learning for the last 6-7 years. My research area is mostly on ML applied to healthcare and medical problems. So basically, how do you take data from the hospitals, for example, from people with various diseases. For example, I was working on Alzheimer's disease or other brain disease, and how do you make algorithms that diagnose automatically, for example, given brain images, for example, or for example, not only diagnose but also give a prognosis, for example, predict the future evolution of the patient, what's going to happen to these people in the future, in 3 months, in a year, in 5 years. I've also worked on image reconstruction problems. So for example, how do you make images, enhance the quality of the images with ML methods, for example, to improve, for example, to make the images better, for example, improve the quality of the scans and so on. But we can talk about it, you can ask me some other time. Just a brief introduction about myself. But welcome to the course. I'm sure you're all very excited. Is this your first ML class, or have you taken some ML before? Which of you have taken some ML before? I see, and done some, got it. So we have a mix, half. Very nice. So, so that's my email address. If you need to send me any emails, but generally for the class, it will be better if you have any questions about the content or material. So first reach out to the TAs and then write on Piazza. So do write all these on Piazza, because everyone can see, my TAs can see, I can see it, and all of you. So basically this way we can all help each other, and we can all answer each other's questions. And we have Piazza. We also activate a Slack channel, so you can use either Piazza or Slack, whichever you like more. But just post there, it'll be much easier. These are the class times, so Tuesday and Thursday from 9:50 to 11:45. It's an in-person class, as you can see. So we'll have a Zoom available, but only if absolutely necessary. So for example, if you're sick one day and you cannot attend the course, then do connect on Zoom. But otherwise, please come in person. I think it will make for much better and meaningful interaction between all of us and between you as well. So you can help each other. So with the material. So yes. So we have 2 TAs for the class, Fateme, Eliassi, and Swati. So one of the TAs is over there, and you'll see her. So she's in the back in red. You'll see her, and my other TA is not here, but they'll both be here from next week. We'll also have 2 tutors and graders to help us. So we're getting quite a lot of help. Before I go, can people on Zoom hear me? Is everything working okay on Zoom? Yes, okay. I see several thumbs up, great. So we have another around 10 people on Zoom right now. Okay, they can hear, they can see, great. So lectures and office hours. Mainly, so I, of course, keep your conversation respectful and polite in general with all these office hours and lectures. So be very nice with each other. So of course, I will, if somebody is is not being nice to you, please come to me and report. Attendance is required. An active class participation will count towards your final grade. But don't worry too much about it. It's not. Essentially, we will have some points towards class participation. But if you are sick at some point and you have to, you cannot make a class, that's fine. Lectures will be video recorded and made available after the class. I'll do my best to make sure that we have everything, recordings and Zooms and stuff. It's also the first time I'm teaching, so kind of give me a bit of time to get familiar with all the systems. So these are the office hours for for all three of us. Actually, I might mine might have updated. I might change mine to Thursday. I'll get back to you. But all of these will be posted on Canvas. So on Canvas, I'll show you in a few slides. It will be the most up to date. So do not, if there's a conflict between what the slides say and what Canvas says, use the Canvas information. So that will be the most up to date. We will have lab sessions. So initially we'll start with 3 lab sessions that will be hosted by my TAs, Fatima and Swati. And one of the office hours will be used towards that. So I think it's the Tuesday that will be done. So the Tuesday office hour, we'll post on Canvas everything again. So I think this Tuesday 1 to 3 p.m. will be a lab session and discussion session. So here in the lab session, discussion session, what we will do is that we will in the first 3 weeks, we will basically go through, like, for example, how to run a Jupyter notebook, how to, for example, like train an NML model, how kind of getting you set up, maybe even how do you upload an assignment, all these things. So you have like you get to and understand like all these things. Yeah, tutors. So we have tutors to grade the assignments, and they might even host, even tutors might host office hours to address any questions related to grading. So the tutors will grade your assignments. Yes, we have an online meeting, online class. Yes, so I'm streaming on Zoom, and we also record. Yes, so as I said earlier, so with emails, it will be much better if you post on Piazza where everyone can see. So this includes me, my TAs, and everyone. Unless there's something sort of like that is like a more sensitive question that reveals private information about yourself, then of course you can post anonymously on Piazza. So you can also choose option to post anonymously. We'll also enable Slack for asking questions. You submit your assignments on Gradescope. And my TAs will show you in the labs how do you do that and how that works. Yeah, and make sure you check your access. So you check your access to emails regularly. So this is what I want to show. So all of this you can't see with the resolution, but basically on Canvas, on the home page, if you go to the first tab in the home page, you cannot read it clearly, but it's probably better here. So you can see that all the all the up-to-date links with everything. So that's where will be the most up-to-date information. So including the office hours, the Zoom links, and so on, and then the slides and assignments. Any questions so far? No. Course evaluation. So we'll have a midterm exam, which, sorry, there's a mistake here. So we'll be in person. We'll not be connecting on Zoom. So this will be in person in the class. I don't know why I had that. So this will be in person during the class on a Thursday. We have exactly the date. There will be 5 assignments, which will count 12% each in your class, and this will contribute equally towards the final grade. We'll post them on Canvas. So assignment 1 will already be released after today's class, so you can already start working on assignment 1. And also we'll have around 10% of the grade. 10% of the grade will be towards participation. So here it is more like lectures, class exercises. I will do some class exercises coming up from next week. So mostly those, and it won't be too hard. So don't worry about it. This is more essentially to get everyone, to collaborate, to work together, for example, and on these exercises, and the discussions, attending invited talks. We might have one invited guest lecture later on. I'll come back on that in one of those classes in week 7 or 8. Yes, okay, so what is this course about? So before, let me say what this course is not about. So it's not about databases, it's not about data mining, it's not about data processing, it's not about data visualization either. So it's not any of these things. So you will have to do some of it, perhaps a bit of data pre-processing, for example, in the assignments, but it's not what the main course will strive to teach you about. This is something that you can actually learn very easily in other courses, in maybe like a more Python course, or and we can learn it also easily from tutorials on the internet. So or even in general coding a deep neural network, we sort of like, we have a mix of theory and practice, but we want you to understand fundamental concepts about machine learning, not just about how to code it up, because you can pull out the code from GitHub of any machine learning model and then run it, and yeah, that won't be too hard. So, but we want you to understand the fundamentals of ML. So these are the planned topics that tentatively that we want to go through. So first we'll start with so this week will be basic concepts of machine learning, and let's say if we finish everything today, otherwise we'll continue on Tuesday. Afterwards, we'll go through a review of probability and linear algebra. So here, this is like I'm talking about expected value, variance, all these estimators, biased and unbiased estimators, and so on, like for conditional probabilities, joint probabilities. So we'll go through that to give a review. We're sort of assuming you know this or some of it, but just in case, we'll go through it again. And also linear algebra. So here we'll go through things like matrices, matrix multiplication, matrix inversion, singular value decomposition, eigenvalues, eigenvectors, all these concepts. So again, we're assuming you know them, but just in case, we'll go through them. And so please, if you have some time by next week, do revise some of these. Actually, that will be super helpful, because these are fundamental concepts on which we'll then build all the machine learning theory that we'll study. Then we'll go into regression optimization. So we'll do linear regression or distributed regression, risk minimization, stochastic gradient descent, SGD, stochastic gradient descent. So these are optimization techniques that once you give an architectural model, how do you optimize the parameters to arrive to the perfect parameters. Then afterwards we'll go to perceptron. So and this is like a type of linear model that was initially that started like a neural network, sort of like a field of research, and then a support vector machines, which is a type of kernel machine, and we'll study that afterwards, and then we'll study kernels more generally. I won't explain right now, but you'll see what that is about. K nearest neighbors, we'll do naive Bayes, decision trees, clustering, expectation maximization. These are, and for example, so EM and clustering are a type of unsupervised learning methods. So these are methods that do not require any label data to learn. They learn a representation. So really powerful, really interesting techniques. We'll do boosting as well. We'll see what that means soon. We'll do special topics. So here I have special topics, but we can do a guest lecture also. So yeah, week 8 reinforcement learning. We'll have a guest lecture. So week 9 a guest lecture. And on 17th of November we'll have the midterm exam, which will be during the class. And I correct the typo from the slides earlier that I said it was on Zoom. So no, it will be. The course was taught on Zoom last year, so the midterm exam was on Zoom. So that's if there's any DRC students in the classroom, please email me. Just so I know to accommodate you for the midterm exam, because you'll need extra time. So do let me know in advance, or somehow maybe reach out to UC Santa Cruz offices, and they will reach out to me directly. So either way, but we will have to accommodate you. So if there is any of you who are DSC students, and week 10 we'll do neural networks, and then we'll have Thanksgiving. So we'll have a class off. So Thanksgiving fall on a Thursday, so we won't have a class then. And then in week 11, if we have time. So this is again tentatively we can go through generative adversarial networks, so GANs, and maybe we'll do another special topics class. So here could be, for example, I can tell you a bit about my research if you're interested, or we can read a paper about like a latest sort of like machine learning model, anything like, for example, DALI, or anything you would like to read. So we could do something like this. How does it sound? Good? Yeah? So, so a brief introduction. So, I've already, yes. One more thing about policy. So more like this is a bit of classroom policy, but again, I'm not too strict. And essentially, when you ask questions, I think quick clarification questions are really welcome. If it's something more in depth, for example, that you want me to repeat something like, and I can, but if it's something short, I'll definitely do it. But if it's something too long, it'll be better to do it in the office hours. So if you come back and you, like, for example, you fell behind the class or you missed the last 20 minutes, it'd be better to come in the office hour and we can clarify it then. And any other logistical questions, again, office hour, Piazza, or email. So what is machine learning? So it's essentially this process of learning where we have, for example, 3 components. We have, so on a brief overview, so again, we have some data and we have an outcome that we want to predict. And here machine learning is essentially the learning part which takes in the data and gives you the outcome. So we do require these components, first of all. So most of the class will be still about data-driven methods. Will not be about, so these are all so we need data, and we need an outcome, a prediction, a variable. We need to tell it what to predict, something to a particular, for example, if you have an image, you can predict the object in the image. If you have a game, you can predict the next move in the game. So like a chess, for example, so you can predict. So it needs something to predict, so that we have to specify. And we see, in particular in the press, all these kinds of like articles about how AI and machine learning will change everything. For example, how DeepMind is making gigantic leaps in predicting, for example, protein folding. And all kinds of like, smart analytics as well. Like, there's a lot of AI even going on in your phone, for example, to make recommendations on your feed. So all those are decisions, for example. So what your social media feed gives you is running an AI algorithm in the back scene, because that's essentially giving all kinds of, based on your preferences, it will tell you, it will decide what to give you. So what is data? So it's kind of like a vague term. Or data, well, it can mean all kinds of things. For example, it can mean images. For example, like for example here, like, and we have to identify the food in the image. For example, it's a hot dog. It's all this like it's all the pixels. So in this case, the data would be represented by some millions of pixels in this image that represent the data that the ML is going to use. It can be text as well. So all this dialogue, for example, that's data. It can be, for example, if you want to do a spam classifier. So you have emails, and you have to predict a spam classifier. This is spam or not a spam. This is this is data as well. So this is what I mean by data. Can you see the screen? Because I'm aware there might be a resolution problem. You cannot see it. It's that one can see, yes. So I think it's because of the adapter. So we'll have to. I'll fix that by next time. I brought mine, but it doesn't work, and that one doesn't work either. So I'm sorry for this. But you can see. Can you see that screen on the back, roughly? Would you like to come more in the front, some of you, that you cannot see, or is it okay there? Okay. Sorry about that.
The bigger text looks alright, but the smaller text on the top.
Got it. Yeah. So it's an introduction class anyway. It's more like a lot of pictures, but yeah, I'll try to look into it. So how do we represent data in practice? So for example, one way we could represent data is, for example, we can actually like plot it on different dimensions. So for example, here we have one dimension on the x-axis, another one on the y-axis, and or x1 and x2. And here, these could be features that we extracted from spam emails, for example. So emails that had spam on, and we want to classify and predict whether emails are spam or not spam. So this is one way you could represent data. So you could visualize it like this. Another way you can represent data is in a table format. So for example, so we have our matrix. So then matrix here. So then we have a matrix X of input features. We have Y and another vector Y of output features. So they could be 1 or 0, for example, spam or not spam or something else. And here this matrix X will so for each row will represent a different data point, and each column would be a different dimension of the feature. So then, for example, if you have X could be different people, person 1, person 2, person 3, and the Y could be different characteristics of those people, like the most recent payment, months paid in full in the last 6 months, annual salary, and so on. So, and you can make predictions about about that. You can present it as a table as well. So here these are genders, also whether they own a car or not, and you can do all kinds of representations. This is, for example, an image representation. So here we have an image of the digit 7. And you can see, so the key concept here, for some of you who have not worked with image processing, is that each of these is a pixel that takes a value. So it could be from, so here from 0 to 255 for grayscale. And if it's color, then you have like 3 channels RGB. And in practice, this is how the computer sees the data. So it just sees a big array of numbers. To the computer doesn't mean anything that this is a 7 or something like that. It doesn't understand. The computer doesn't understand that this has a digit in the image. This is what the computer sees on the right. So, and the key task of the ML model is to take this image here, this representation, and predict that this has a 7, digit 7 in it, and that's quite hard. So we as humans, we cannot do it easily. So that's why, yeah. So it's complicated. So I'll skip some of these. And there's all like other kinds of types of data. So we can have categorical data. So different categories. So animals, for example, a fox, a bear, and so on, a cat. We can have ordinal data. We can have quantitative data. So here ordinal would be, for example, like that show the order, for example. So you have like it can be a ranking, for example, like rank 1, rank 2, rank 3, this kind of stuff. Yeah. It can be quantitative. Yes. So all kinds of types of data. So what do we mean by supervised learning? So there's several types of learning here, and we'll start first of all with the supervised learning, which is kind of the simplest. And ignore the batch word for now, because I'll explain the batch in a second. But what do we mean by supervised learning? So so first of all, we have in practice we have an unknown distribution of things from which the data comes from. So this is an unknown distribution of the data. So the data is basically an instantiation from this distribution that it was sampled from. That's the first thing. The second thing is that we need to have both attributes. So these are the inputs, and also attributes or features. And we also need to have labels. Why? So these are labels. So essentially, from the attributes of the features, the ML model will try to predict the labels. And here these labels can come from a teacher. For example, so I as a human can tell them the model these images have a cat or a dog and so on. And the instances are again drawn from the distribution, from this unknown distribution that we're sort of trying to learn. And these so these attributes or features are along with the labels are called the training set or the sample. So here, this is the set that you use to train the model. This will be a data set, and you train the model on this training set or on this sample. And what I mean by batch is that the training process will occur in batches. They won't take the whole data set at a time. They will take small chunks. First the one chunk, and then process it, and then a second chunk, and process it, and so on. So it will do in these batches. So that's what we mean by batch learning. So supervised batch learning. And the key idea is that you need to create a hypothesis, a rule or function from the sample. So here the hypothesis is is generally given by the, for example, in the case of neural networks, is given by the architecture, the type of like architecture that the model has, or the family class. So some people call it the family of functions that they can model. For example, so the architecture of the deep neural net, for example, will encompass a certain family of functions that they can learn. Because what I'm trying to make a distinction here between the family of functions that, for example, all the deep neural nets that they can model, and the actual parameters that instantiate a particular. So once you train a model, you learn some parameters, and those instantiate from that family of functions. You choose one of them. You choose one, and that will be your model that you train. So. For example, let's think about it. So, for example, if you take linear regression, so for example, the models are linear, all of them, and you have two parameters, ax plus b. So the parameters are a and b. So ax plus b equals 0 or another constant. So 0 actually. So a and b are the parameters. The family of functions are all what we mean by hypothesis of family functions are all the linear functions that could possibly exist. And once you instantiate them with once you train, you learn the parameters a and b. So those are the parameters and then they fix from all the families of all linear functions. You fix to one linear function, one particular one. So yes. So there's several types of supervised learning that we can do. So one of them could be classification. So here again, we predict labels that are nominal. For example, they're discrete categories. As I have in the slides here, ham and spam, or Democrat, Republican, independent, for example, if you want to do all kinds of discrete labels. You can also do binary classification. Again, another type of classification is 0 or 1. For example, if the email is spam or not spam, that could be just two classes. Sorry. We can do regression as well when the labels are numeric. For example, so if you want to predict the price of a house, so you study the housing market in the U.S. Which quite now is and we're trying to predict essentially the price of a house, for example, and you can predict now in the present or also in the future what's going to be the price in a few years. So this is a regression problem because the price is a continuous variable. We can also have ranking problems, so we can order. So here ranking problems are very common. For example, again in your social media feed, it will tell you what's the first feed item that I'm going to show my user. What's the second one? What's the third one? So that's a ranking problem that we can do with supervised learning. So yes, so classification, again, as I said earlier, these are, for example, types of regression models. So again, we have a house, for example, from just a picture of a house. For example, for the picture of this house, we can predict what will be the price, for example, of the house, just like that with the machine learning model. Or this is an example of a ranking problem. So again, you have. Sorry for the resolution if you can look there, but it's different searches on Google. So on Google you get different search results, and it orders which one is which, basically. So which one is going to be the first result, which is going to be the second result, and so on. So why do we want to learn? So I'll ask the class. Why do we want to learn? Let's hear some answers. Yeah?
To predict the behavior.
Why do we want to predict?
We want to know the results before. We want to know the results.
We want to know the results of the future.
Which we don't know. Before by predicting what happened before and what can happen in future.
Yeah. Why do we want to predict? Why are we interested in prediction in the future? Why do we want to predict the future?
To make our life easier.
Yeah, to make our life easier. That's a good answer. Yes. More precisely, more specific.
I just want to save time.
You want to save time.
So if we have new observations, we can directly predict from what we have learned.
Yeah.
We don't have to learn again, right?
Uh-huh, uh-huh.
So on new observations, we can directly get the results. So that will save time. And
Save time, yes. Yes, yes. Any other ideas?
Make intelligent decisions.
Make intelligent decisions? Uh-huh, uh-huh.
data is too hard to model nowadays.
Data is too hard to model, okay.
Getting increasingly harder to model.
Uh-huh.
So it's like we can manually model like programs to fit to the data, but as data grows and becomes more intricate, like difficult to understand, machine learning helps us.
Yeah,
make
yeah,
sense of
yeah,
it.
yeah. Yes, yes, yes. Let's hear more from the back. Another one or two answers from the back. Yeah.
Automate tasks that we had used people for before.
Automated task that people have done before
That we would have to use like.
that we'll have to do many times repeatedly. Yes, yes, yes. That makes sense. These are all really good ideas. That's exactly why. That's exactly why. These are all yes, yes. Even save people's lives, like like in my research. So you wanna make a predict for a patient in a hospital. You want to predict what's the diagnosis, what's going to happen to them in the future in a year. So to give them the right treatment. So to give them the right treatment to help doctors in giving them the right treatment, for example, so they save their lives. So. And one thing I suppose actually did this last bullet point. I wanted to say a few things. So for some problems, there's no need to do machine learning or AI. For example, to calculate payroll, we do not need, because it's first of all it's a simple process, and we know we have exactly the right procedure to calculate it. We know exactly how to do it. You take all the months, you sum them up, you do the taxes and so on. You take the percentages. We know all of that. We do not need to learn this process, to relearn it again. We already have it. So for some problems, you do not want machine learning, or it depends, especially if you already have a model that can take you from the inputs to the outputs, and it has the right properties, let's say, then you don't need you don't need to run ML or run AI. I'll give another example, which is more, for example, in computer graphics, people do like, for example, like effects. For example, like they create effects of smoke, for example, in computer graphics. So then, like, you have like a 3D scene, you create some smoke, and then so would we want to use ML or AI on that? No. So I see a no.
So the reason is that all those smokes and lighting and shading things are kind of already defined by mathematical curves.
Yeah.
So
Yeah.
machine learning is not at all
Yeah.
required.
Yeah.
We can just set the parameters on our own.
So exactly. So there's some mathematical models that can simulate the smoke already. So they use the fluid dynamics, fluid mechanics, Navier-Stokes equations, for example. There's some other equations. You implement those. You already have the model in those Navier-Stokes equations. You put the smoke particles in the virtual space, and you run over time. You integrate. You run the differential equation, and you integrate over time, and then you have the model. That being said, the reason why I chose it is it's a bit of a tricky example. However, even though this is the case, some people still use ML or AI. There's people have done, for example, to do these simulations. Why do you think that's the case? Yeah.
I think, I mean, even for the smoke thing,
Yeah.
it's easier for us to formulate that for a computer to learn how the behavior of an unknown thing is, so that we can, kind of read the data and kind of conclude how that mathematical function operates. I mean, if you take a look at the smoke, when it comes up, it rolls around and goes up. So I think it would be easier for the computer to come up with a pattern that is showing up some type of function that the smoke is, kind of following as a behavior.
I'm not following you. You're saying that it will be difficult for a computer to find a function?
No, it's going to be easier for the computer to do a huge brute force, data processing in order to figure out what kind of function is smoke following that is, kind of creating this type of pattern or behavior. Yeah. We do know the functions though, so we do know it. Well,
and
let's
it
assume that there is
there is
some unknown
I know.
thing
Yeah. I know. I get it. Any other? There was another, yeah.
To get approximate results more quickly.
Yes. So to get approximate results more quickly. The problem also with these simulations that they take a very long time. So to do that simulation of the smoke could take days, weeks, even on some really fast hardware. It depends, especially if you want to do something really, really complicated with millions of particles or billions of smoke particles, if the scene is too complex. If you want to get results more quickly, you can approximate the process with machine learning, and then you can get them in a few minutes. So that's the reason. So speed. Even though we know the model, we can approximate it and run it much faster. So with ML. A few more ideas. So another learning is also often used when human expertise does not exist. So for example, we navigating on Mars, for example. So we don't know how to do it, like even us as humans. Or again, navigating in a really unknown environment we haven't been before. Or even when, for example, humans are unable to explain their expertise or decisions. So speech recognition, object detection. So if we look at an image, we cannot explain how we do in our head, how do we decide, how do we do the processing and see that identify the objects in that picture. We just do it somehow by magic. So also when solution changes over time, so it's routing on a computer network. So these are also very important. So when packets flow on a network, for example, in the web, then the flow of traffic changes really dramatically, even over minutes and hours. So then, like next time the same package will be sent, it might be sent on a different route because one route got very congested. So yeah. So these are other examples of when we don't have a model and where we need to do learning and do machine learning. So when we talk about learning, what we actually talk about, so we're learning general models from a particular set of examples. So in the end, we still have a few data points, and we're learning a generalization of that, of kind of like how to reason about this data, how even this data came from. So we can learn, for example, generative models, which kind of like can generate new data. So you have a set of images with adults, for example, or like with the human faces, or with brains, in my case, or with the brain images. So it can generate new images like that, like new brain images that were not in a data set, a new picture with the people that don't exist. So you might have seen of the deep fakes, for example, like all these like images generated by AI methods that look really of humans that look really realistic. So yeah. So to generate a representation of the data or prediction. So either to understand the data and generate a representation or to predict it. Let me see. What we talk about when we talk about learning. Yeah. So in general, nowadays data is cheap, and we have like a lot of data from the internet. For example, we have a lot of data in medical centers, in hospitals. We have a lot of data, sound data, and so on. So, but knowledge is expensive, and so basically knowledge and expertise, that's quite expensive. So, for example, it's really expensive these days to have to label data because you need to hire humans to actually like annotate all those images. So that's a very expensive process these days. So. For example, I remember when ImageNet came out, this large data set of images came out in 2009. The research group, for example, at Princeton, who did that, they had to hire people from Amazon WebTech, for example, to actually annotate them. And they hired like hundreds of volunteers, basically, so to actually annotate those millions of images. It was a lot of effort, so it could not be done by one or a few people. So, and we need to build a model that is good and useful approximation to the data. One second, let me see. Let's do a few more minutes, and then we'll take a break shortly. How about that? We'll go through a few more slides, and then we'll take a short break. So what is machine learning? So we have training features X, and we have labels Y. and we need to optimize. So this is what we're talking about, and we need to optimize the performance criterion using these examples. So we need to define a loss function, and we'll talk about it later. There's a role of statistics. Yeah, so we can do inference from a sample. Role of computer science. Yeah. What is not machine learning? So sometimes statistical machine learning is not, for example, cognitive science. At least not like in its traditional sense. People can combine. There's been some inspiration from cognitive science that goes into the designing of these methods, and sometimes you can, but it's not. Yeah, it's not cognitive science. It is related to statistics, to data mining, knowledge discovery, knowledge representation, control theory. So, for example, the optimization methods of that stochastic regression and so on is somehow related to control theory, but we won't go into that in the course. And it is part of AI, but not traditional AI. Traditional AI is what often it comes to, for example, a symbolic AI is what people think of when you say traditional AI. It's more like using symbolic rules and like a knowledge representation rules, for example, to make inferences. So, for example, you have like A implies B, B implies C, so then you can deduct A implies C automatically, you can infer that. And you have a knowledge of these rules, a knowledge base of these rules, and then you can run inference. But this is not what we will do. So we're not doing that in this course. And there's also, I should say, also like adversarial examples. So, for example, there's instances in images where, for example, you have an image and you add a bit of specially crafted noise, and then this can it's still going to be a panda bear, but now this will fool the ML model to predict something else. So instead of a panda bear, it's now going to predict to be a gibbon, for example. So these are, for example, like this is an active research area also in machine learning, and people are trying to understand why this happens. And we have some ideas, but we're not fully there yet in terms of understanding of these techniques. Let's take a short break here. I'll stop here. Let's take a short break, 5 minutes, and then we'll resume afterwards. Yeah. Hi.
I really wanted to see if I have a doctor's appointment at 11, so like I was wondering if this class would be like recorded.
The class will be recorded, yes.
Okay.
Yes. So
Thank
yeah.
you so much.
Yeah, I'll post it on Canvas. So go on Canvas, and you'll see again on the homepage. You'll see all the links. I'll post the recordings there.
Okay. Sure. Thank you.
Yeah. You're welcome.
I missed the first 15 minutes.
Yeah.
Sorry.
No worries.
Did you just go over this, or did you go over like a syllabus or anything?
It was mostly logistics. It was kind of like, when at the classes, when at the office hours, kind of like
Okay.
exams, grading, kind of like that. Yeah. So you can see that in the slides, but it's not much. It's kind of like, where the office, when the classes are, and the office. Yeah, that's fine. Yeah.
And then it's on Canvas, right?
It's all on Canvas. Yeah.
Have we been added to the Canvas? Because I don't think I saw it last night.
I published it. You should be. Let me know if you don't. Like if you don't manage to log in, email my TAs.
Okay.
And they'll help you. Yeah. That's the best. Yeah.
Okay. Thank you.
Yeah. So you're welcome. Yeah. Yeah.
Being late a little bit. I'm coming from Monterey, and I got stuck in traffic jam.
No worries.
I mean, there's sometimes machine learning.
Yeah.
Classes got always
No
a
worries.
bottleneck,
No worries. Yeah.
So sorry about that.
No worries.
You don't get offended if I have my hat on in the class.
Not at all.
Yes, sir.
Yeah. No worries. What's your name?
Mike
Nice to
Angelmani.
meet you.
Nice to meet you.
Nice to meet you. Yeah. No
Yes,
worries.
sir.
No worries.
I Googled your name,
Yeah.
and your credentials popped up from university. You've done it in England, right?
Yeah.
Okay,
Yes.
okay.
I spent 8 years in the UK in London.
Oh,
I did my
okay.
undergrad
Royal
and the
College
PhD
London?
there. I did my PhD at UCL, my undergrad at Imperial.
All
Yeah.
right.
Yeah. Have you been? Have you?
My father-in-law is
right.
graduated from
Right.
Royal College. He did his medical in there.
Yeah.
Yeah, but
I
I was
know,
in
yeah.
Germany. You know.
Oh really? Oh wow. Oh, that's great.
Your heritage is from Romania, right?
Yes.
Okay.
Yeah.
It's very similar to the name family names of my friends in
Ah,
Germany.
really? Yeah.
Are you fluent in that language?
I can speak some German, and oh, you mean Romanian? Oh yeah, my native language. Yeah.
Okay, great.
Romanian. I grew up. My family is Romanian. Yeah, I grew up in Romania, and I left when I was 19. So right when I finished high school.
Okay.
Yeah.
I have friends from Bucharest and
Yeah.
Iași.
Oh yeah.
What part of that country are you from?
In the south, so Pitești is an hour from Bucharest.
So
It's in the south of
close to-
Romania.
to, Hungary is here, Romania is here.
Yeah. So it's
Moldova
closer
is
to
here?
Bulgaria.
Bulgaria, okay,
Yes.
okay.
It's in the south. Yeah, it's like an hour from Bucharest, from the capital city.
Oh, right.
Yeah, so it's in the south. Yeah. Well, what do you do?
I'm a Navy veteran. I finished that and I was working at DLI as a language teacher for 9 years and a half. And my background is linguistic, but I switched to computer science because as a hobby I was doing it forever. You know, trying to get a job
Yes,
in computer
yes,
science. And
totally.
Since I was interested in electronics as a hobbyist and stuff, I switched to computer engineering. So
Yeah.
Here I am, finished it halfway. I got lucky for this class because it was not popping up for some reason.
It was not a.
It was not popping up.
Popping up.
Yeah, when I was trying to add, it was not showing up in there. It did it once, and then I signed up for it right away, and it didn't show up again. I don't know.
Yeah.
So,
That's okay. But you're fine now. You're on Canvas. You have access
Yes,
to Canvas.
yes. I
But
did
that's the main thing. The
syllabus
Canvas.
and the quiz and
So the Canvas, because you have all the materials there. Like the rest of the stuff, like I put the links there, so you have on Canvas.
I
you have-
downloaded the book and everything.
Yes, the book.
I
Yeah.
believe Python is the only requirement that I would need, as a prerequisite.
Go to the labs. Go to the labs. There'll be 3 labs like that my TAs will run. So then you can they'll go through Python. They'll teach you even a bit of Python if you need. Running Jupyter Notebook, and so that'll be really good idea actually. Yeah. Go.
And you got
make sure that-
office hour today at between 4 and 5, right?
Oh, I was thinking of starting from next week, but I can do because I don't know if we kind of need. Yeah, I'll do it. If you want to come, I'll do it.
Yes.
I'll do it. Yeah, I didn't specify, but I'll do it. Yeah.
Thank you so much.
You're welcome. Yeah. Come over. Come to the office hour. Yeah. Can you guys here in the back hear me and like see?
Yeah, we can hear you fine.
Okay. Oh,
Yeah,
you
we
can
can
see. You can see. Okay. Okay, shall we resume? So we've been talking about so far about input X, labels y, we run a machine learning model that can take us from x all the way to y. So here, what we mean by the learn model is this function f that takes us from the inputs to the outputs. And this is again also called the hypothesis. We also call it hypothesis f, and this is defined by parameters. So for a deep neural net, for example, the parameters will be all the for example, like the convolution parameters that it applies. For we'll see for other kinds of models, they'll have different kind of parameters. So for a linear model, as we said, we have the a and b, for example, are the parameters. And how do we learn the parameters? So generally we optimize a loss function. We have to define a loss function that we then optimize to find the optimal parameters. And one of the main reasons, I should say before we even go to this slide, one of the main reasons why we need the loss function is because we don't have an analytical solution to many of these models. When you optimize a linear model, for example, which has just two parameters a and b, you can find an analytical solution right away. So given 2 points, for example. But for many of these models that we study, we do not have, ideally we would have an analytical solution, but we don't have. So that's why we have to define a loss function and then optimize that. So we do it with optimization methods. So we define the loss function, which we'll call, for example, L, between the y's that are from the data set. So these are the labels that come from a data set, and the predicted labels, y prime, for example. So these are the labels that our machine learning model predicts. So and the loss function generally tells us how good the function is. So once we have a particular function with a particular set of parameters, it tells us how good that is, or good or bad. And these are all different for different ML methods. So for example, for a classification loss, like a very simple loss function would be to put a 0 whenever the labels don't match, and to put a 1 wherever they do match, for example. Whereas a regression loss, for example, a simple one would be the L2 distance. So this is the squared distance between the y and the y prime. So this is, for example, with the house prices, you predict a particular price, 100K. The actual price was 150K, so you subtract that, so you get 50K squared. So that will be your loss. And we will see more examples of this into the future. And minimization is done with an algorithm like gradient descent. So we'll see, and it's actually also stochastic gradient descent because it has a stochastic element to it. We'll see that very shortly. But the idea is you compute a gradient, you compute a derivative of the loss function at a particular point in your space, in your parameter space, and then you go in the direction of the gradient which minimizes the function. And in general, I want to say that learning is a very ill-posed problem. So if we assume nothing else, we can anything can happen. Basically, any label can be predicted in theory. So for example, I'm showing these pictures of 2 cats, for example, but you can imagine that a particular ML model, if we don't assume anything, it might also think this is a tiger, for example. So especially by the particular kind of like stripes here, like the fur and so on. And maybe it could be a baby tiger. Who knows? Like, I mean, even for us, like, it does look like a cat, but who knows? It could be a baby tiger. We have to assume something, so that we have to make some assumptions. So, like, without having any assumptions, you cannot do any learning. You have to make some assumptions, and people also call them inductive biases. And we'll speak shortly about inductive biases and give an intuition of what that is. So this is what I'm talking about. So we need an inductive bias that limits the potential connections between these x's and y's. So does anyone have, which of you have a vague understanding of what an inductive bias is?
I do have some understanding.
Okay, so very few. So it's essentially, as I said earlier, without making any assumptions, we cannot do any learning. Then remember what I was saying about talking about families of functions or hypotheses. For example, this is, for example, when you do, for example, like learning with like a linear model or like for example, even a polynomial, for example, you try to fit a polynomial onto data points, then, for example, if you choose a polynomial, you are restricted to the family of polynomials. So that's an inductive bias, like the fact that you set to learn a polynomial function. And this could be represented by any kind of parameter. So I'm not talking about the parameters here, like if you set those polynomials can fluctuate widely, but you're still constrained to a family of polynomials. So then if you want to model, for example, an exponential function, you cannot unless you take an infinite series, or say you have a linear model, then you're only constrained to linear models, the family of linear models. If you have a nonlinear problem you're trying to learn, it would not work. So that's the inductive bias. The inductive bias is like, for example, the fact that you're training a linear family of functions. Yes, so for example, neural networks have an inductive bias, for example, because here's a question there.
Is there a relation between inductive bias and correlation and causation?
No. Inductive bias tells you a bit about the family of functions you're trying to fit. Correlation is this concept of, for example, the data is highly correlated because the functions it came from, the distribution it came from was highly correlated. It was a highly correlated, for example, distribution, or it came from a data generating process that correlated them. Causation is another concept I wish we had more time to go through these, but causality is basically the idea that you have a data generating process and that comes in several steps, step A, step B, step C, and sometimes these are causally independent with each other. So step A is independent from step B and step C, so and so on. So it's they're all they're different concepts. We can talk more you can ask also, like, we won't have time to go through these in the course, not through causality. This is, but you can ask me in the office hour if you're curious about it. And it's also a Bayesian approach. So, did any of you work with Bayesian models? Which of you worked with Bayesian statistics? No, just a few, just 2 or 3 hands. So Bayesian methods. And I like them a lot. They're really nice. They basically define a prior over your parameters or distributions, and then you use something called the Bayes theorem to learn a posterior. And we'll talk about that later. But essentially, we'll go through Bayes theorem. But it's basically a much more solid approach to reason about uncertainty. So uncertainties in both the inputs and the outputs, because oftentimes these problems are very ill-posed. There's multiple solutions, for example, to one particular input prediction. So if you work, for example, with images, you try, for example, to do something like in painting is called. You have half an image, and you try to complete the other half. There's multiple solutions. For example, the other half of the image could have another tree, you could have 2 trees or 3 trees. Any of them are equally likely. So then you have to talk about distributions of solutions and uncertainties over them and so on. Which one is more likely? Which one is less likely? So that's when Bayesian approaches are used for. So choosing a hypothesis space. So let's see, how do we choose a hypothesis space? Let's understand this a bit better. So imagine you have a set of points. These are points distribution, and you have a particular function here from which you sample like a few, and these are, for example, from class A, and these other ones are from class B. So this is your true function. This is like the function that you don't know. So in practice, you do not know. You only observe the data points, and so this is f of x. Remember, you do not know f of x, and you're trying to fit another model to understand, so g of x, and this is g of x is the model we are going to fit. So, for example, if you choose a linear model, for example, that is very simple, then, for example, we can try to fit a triangle onto this. It will never perfectly work, even though as much as you move those edges, for example, this triangle, like you'll never be able to fully approximate the square, first of all. You might be able to capture all the data points, but not necessarily. So here, for example, you see we capture all the data points we were interested in, but we also have a few extra ones here. So it does. So this model is too simple, and it overgeneralizes. That's what happens. So the model has more what we call more bias, but it has less variance. So the bias here is that it makes it's much more rough. It kind of like it tries to simplify too much. For example, we can also choose a hypothesis space that is too complex, so to go to the opposite way. So then we try to fit like a really complex model with like all these kind of like really accurate contours, and then we can capture the data very well, but it won't generalize well. For example, like it might miss out some of these other spots. It still doesn't fully capture the square. So remember that the square is a true model that we're trying to learn from the data, but we never know the true model in practice. We only see these data points. So this model, this more complex model, we call it has less bias but more variance. So these are kind of like concepts, and this is called the bias variance trade-off. Sometimes you can have a model that is too simple, so like the triangle, which has more bias, or too complex, which has more variance. Does it make sense? So let me show you another example. So just to make sure we clarify what we mean by bias and variance. So this is, for example, our training data, T1. So we have red dots and the green dots. This is the model we learn. So everything inside this shape belongs to the red class. So this is our data set. Again, A's and B's, two different classes. We learn this model. Now, what really happens in reality that we don't actually, we have to be aware, is that this data set that we collected comes from a much larger instance space. So there's actually many more points in practice that we haven't collected. So for example, we only study, for example, like we do a population study and we only choose 100 people, or like, so we have 100 data points, but there's many more millions of people in the United States, for example, in the world, billions. So we have only a small subset, but actually the instance space is much larger. So then what happens is, if we chose a different set of a different 100 people for our data set, for example, to collect, this could give us a different model, for example. So now we, from the same instance space, we chose a different set of 100 people, and we get a different model now. And this is for example, so this is the difference between them. So on one side, initially we get this model, and this is the same model family, the same procedure, just the data instantiation is different. So we have different training sets. And they both come from the same underlying population, from the same instance space, with just different instantiations of these training sets, and they give us different models. So that's a problem, because then we ideally want to have the same model, ideally. So we want to be very close to each other, but we get completely different models and completely different results. So this is one of the challenges in ML, is basically how do you make sure the model is stable, for example. So then if you take a different kind of, and robust, if you take a different data set that you train it on, is it still going to work and give you reasonable numbers, and so on. So what we mean by inductive bias, again, by high inductive bias, is that the model makes a lot of assumptions. And here, again, these are mostly due to the model family that is chosen a priori. Generally, yes, especially inductive bias, but also bias, can also refer to the assumptions made by the parameters. But that's, so the quality of the classifier can be decomposed into variance and bias. So again, variance represents the estimation error due to data. Bias represents the approximation error due to the model family. We saw this again. So this is a model which has high bias, and this one is a model which has high variance. So a very simple model with high bias, very complex model has a high variance. So, yes, a question.
So determine the bias variance balance, is it a trial and error thing that we need to do, or is it
to determine the bias variance trade-off. Generally, actually, these are more like abstract concepts. You can quantify them, but people don't often quantify them for a particular model. They don't try to estimate what's like a given number to the bias and to the variance. They're more used, more to think about it and think about and reason about the models. You can get some estimates. You can. For example, the bias in statistics terms, like in if you take a course in statistics, it's actually the difference between the bias of an estimator. You have an estimator, you have the true actual value, and that's the difference between the estimated value given by the estimator and the actual true value. So that's theoretically defined, like for example in statistics as such. But here we're talking about bias in terms of functions, families of functions, and that's a bit more, you can also define that, but we're not going to do this in the class. It's more of a way to think about it, more conceptually. So, so is it better to have a more complex model? Not always. The answer is not always, because often we follow what's called the Occam's razor principle. So basically, if we have, for example, two models, that one is simple one, one is a complex one, and they both give the same results, same accuracies, for example, we generally prefer the simpler one, because of Occam's razor, this principle that generally the simpler models are often preferred if you have models that are quite equally accurate. So. And the reason is because in practice they have been found to work better, essentially the simpler models. And there's also like theoretical ways you can reason about them. For example, theoretically it makes sense if you, for example, do something like Bayesian model selection, which we'll see if we get to that in the class. But essentially, there's theoretical ways you can understand why a simpler model is generally preferred. Again, you can ask me more in the office hours, but generally simpler is better. And also in general, real data is very, very noisy. So it's really, really noisy, and then you always have the danger of overfitting. So in this case, we prefer simpler models because they overfit less. And by overfitting, what we mean is that the model is too complex and basically learns the noise in the data, whereas underfitting, so overfitting was this is an overfit model. Basically, the model almost learned the noise. For example, here, whereas this model underfits. So it's too coarse to be able to properly learn the complexity of the data. So that's what I mean by overfitting and underfitting. So. So this is what I've been saying. So model complexity. So this is what this graph is what we call the bias variance trade-off. So essentially we have on the x-axis we have model complexity. So here these are very simple models, and here we go to much more complex models, and the y-axis is the expected error. So this is how much error we expect. So if a model is too simple, then they basically underfit and we have a high error. If a model is too complex, they can overfit. So you've seen these examples here. This overfits, and we still have a high error. And generally, there's a very nice ideal range in between, where here in the middle, where basically the model there. Essentially, that's an optimal. So basically, here it's quite a good balance between overfitting and underfitting. So we want to find these models in this range. We want those models, and we'll see how we will get to them. And I should also specify very briefly that this is also more like of an older understanding. There's some really recent results from like 2 or 3 years ago, which show that even this curve eventually can start if you go to very complex models. For example, for some deep learning architectures, it starts going down again. But this is very recent. These are very recent results from just 2 or 3 years ago. So we won't go to them in the class. But this is still like this is what has been believed to be the case for many decades, sort of, yes, for at least 30 years. It's starting to change, but yeah, so we need to find this ideal range between overfitting and underfitting, so this sweet spot. So overfitting, again, hypothesis is too complex for the truth. Underfitting is when the hypothesis is too simple. And that's the idea. Here's another example of overfitting and underfitting. So you have, and this is actually taken from the Bishop book. So this is a textbook we're going to use in the class. So if you feel free to take that from the library, we're going to follow that. So you have a series of data points. For example, these are the blue data points that we collected, and we fit several models. And these are polynomial models, polynomial functions. So this is a polynomial of degree 0. So it's a constant line. This is a polynomial of degree 1, so it's a linear function. This is a polynomial of degree 3 and 9. So you see how some this one is underfitted, right? You see how essentially it's not able to capture the data, the complexity of the data. Whereas this one, for example, overfits too much. So you see how it kind of like it jumps away too much instead of staying quite smooth. So for example, in this case, something like m equals 3 seems to be like an ideal sweet spot here. With it's a function that kind of it seems to be the best for in this particular case for this family. Does it make sense here so far? Yeah. Questions? No. How do we find the ideal range? So how do we find this sweet spot between too simple models and too complex? So generally there's several ways you can do it. We can basically start training the models, and initially they'll be kind of like as the training process. Initially they'll be very simple, and later on, as the training progresses, they get better and better at fitting your data. And then they eventually overfit. They might even overfit. So then you can, for example, stop early. You can do early stopping. So you start your model, your loss function will go down, and it might start increasing afterwards. So you kind of stop. You stop it early. Once, for example, it starts increasing. There's other ways you can do it. For example, you can have a test set. You can do cross-validation, have a separate test set. You split your data into a training set and the test set. And then on the test set, you keep track of the generalization ability. So you train just in the training set, and then you see how it does on the test set. So if the error, for example, increases or decreases, then you can select the model based on that. So these are the two main, for example, ideas. So early stopping and test generalization performance. There's also, of course, these measurements are imperfect and they have a lot of noise, and this can come from many kind of sources. So essentially, they could be, for example, measurement noise. For example, there could be, for example, somebody didn't write the data properly in the database. There could be labeling noise. For example, the human who annotates the data set makes mistakes. For example, in medical settings, for example, the doctor in a hospital can make the wrong diagnosis, for example, and it happens very often. So then when you train the model, you'll have a lot of noise, and these are all sorts of noise, basically, that affect the model. So it's important when you have an inductive bias, then you can deal with some of this noise. You can basically see through, remove the noise and just learn the main patterns with the model. So there's also other kinds of supervised learning that you should know. So there's also reinforcement learning, and we'll go through that in.
Your projector, everything's working okay?
Everything's working okay. Yes. Thank you. So there's also we have reinforcement learning. Where here, instead of, we're actually learning a policy over a particular environment. So for example, this is used in games, for example, something like chess, or where basically you have a whole environment of a game and you have to take actions. Or for example, in robotics, you have a robot that is in a room, and then it has to take, at each point, times it has to take actions. For example, move forward, move right, move left. And this is this is a type of learning that we will also do in the course towards the later part of the course. There's here we don't have generally, so in this paradigm we don't have supervision, we don't have any supervised outputs, but we do have rewards. So basically, if the robot ends up finding something very good, then it can get a reward, for example, if it reaches a particular target state and so on. So we generally give rewards for that, but they're delayed. They don't come, the rewards don't come right now, they can come in the future. So they have to find the right actions to get to the reward. Online learning generally means that you don't have a training data set that comes at you right away. It comes over time. So basically, you learn a model that that adapts over time. So every day there's a new stream of data that comes. You update the model, for example, and with the using that new stream of data. And the key, the trick here is that you don't want to have a model that, for example, every time you have a bit of data coming at you, for example, like that it takes a long time to retrain. You want this retraining to happen much faster and quickly, basically. So you don't have to like. So there's ways to do this with online learning. Semi-supervised learning means that you use both labeled and unlabeled data. So some data sets, for example, might not have labels. So you can have a lot of images from the internet, but only 10% are annotated, for example, as with the objects they contain. So the rest of 90% generally could not have annotation. So then you can use techniques from semi-supervised learning to then use both together. So even to make use of the unlabeled data, because that unlabeled data can tell you a lot about the distribution of the inputs, and that generally helps the accuracy. Can help the accuracy a lot. Active learning is another paradigm where so in active learning you request at each step in time, you request what is the data point that I want to have labeled. So we're in this paradigm like a semi-supervised where some data points are labeled, some are not labeled. Like imagine you have a spam classifier. So you have emails, you want to classify which ones are spam and not spam. So you might have only 10% of them that are labeled. And then what the model does is it tells you what data point do I want to know the label of. So for example, the model can ask you, oh, is this email spam or not? And is this other email spam or not? And so on. So then that's the active learning paradigm. So unsupervised learning is another very big paradigm. So here the unsupervised learning means that we don't have any labels y and annotation labels. So we normally try to understand what is happening in the input data x by itself. And for example, we can do that to learn a representation of x, like a low dimension representation. For example, we want to see particular trends in some data, for example, like also like more high level trends. Or you want to do clustering, for example, so you want to find, you have a population of people, for example, and again, you want to see what are the big groups kind of like that we see from the data. So that's one instance, for example. So here we have two data sets, two clusters of data, and we have two different clusters. And so clustering is a form of unsupervised learning. And there's all kinds of example applications. For example, image compression is like a very big one. So here, for example, you have an image and you just want to compress it and then decompress it at the end. So there's no labels on the image. You only have the image itself. And sometimes you can lose some information. It can be a lossy compression, but generally this is a form of unsupervised learning. Identifying unusual airplane landings. For example, like some airplanes could be landing at an unusual time. We want to find out why. This is a form of what people call anomaly detection. You have a data set and you try to find the anomalies. For example, there's some sort of like to say like find the outliers in a data set. These are the normal kind of like data points, and there's a few outliers. Identify which ones they are. So this is, and we'll do that in assignment 4. So we'll do unsupervised learning in assignment 4. And there's other topics. So of course, data security and ML security, privacy and bias. there's all kinds of problems. For example, this is an example of a model that predicts stop signs. For example, for self-driving cars. So you see, it can predict a stop sign with 99% accuracy, but if you have some kind of slight perturbation to the model, or for example, like you can do any adversarial attack, or if you put some kind of tape on it in a particular position, then the model can be fooled and think this is a sports ball. So then imagine what would be the consequences of this if the self-driving car thinks that that's not a stop sign and a sports ball, then it won't stop and it will keep going. So it's very important to make sure they work well. And there's all kinds of there's also bias, and we'll explore some of it in assignment 5. So we'll explore some of these more niche issues, and we'll work on for example fairness. So that assignment 5 will be on fairness and data bias. So evaluation, so measuring predictive performance. So okay, so any questions so far? Okay, so now for the last few minutes, let me see how much time we have. Okay, we don't have too much. We have only 10 minutes. We're gonna talk about how do we measure predictive performance. So there's several ways you can do it. For example, you can compute accuracy and error rates, and you can also compute precision, recall, and F measures. So the accuracy is generally the number of correct predictions we make over the total predictions. And the error is the inverse, is 1 minus accuracy. So these are two common performance measures. Well, at a high level, to get a more refined error measures, we need something called a confusion matrix, and this is basically it's a matrix which says these are predicted classes and these are the actual classes. So for a binary prediction problem, yes or no, for example. If the prediction says it's a yes and the actual class was also a yes, then we call that a true positive, because the prediction was true and it was also a positive instance of it. Similarly, if the prediction was a no but the actual class was a yes, we call that what we call a false negative. So basically, because the prediction was false and it was actually and it was predicted as a negative. So true negative is again prediction was no, the actual class was no, and vice versa. So if the prediction was a yes and the actual class was a no, that's a false positive. So the off-diagonal ones are false because the prediction is false here. So these are the false ones, and the diagonal ones are true. So so now given these, for example, if you have a table of predicted yeses and nos. So for example, we have 100 true positives, 5 false negatives, 10 false positives, and 50 true negatives. What's the total number of instances in the corpus? So it's just the sum of all of them. Total number of predicted yeses, you sum this column. So this vertical comma, 100 plus 10, 110, and so on. So total number of predicted nos, it's 50 plus 5, 55, and so on. So actual number of yeses, so we sum the row now, so 100 plus 5, 105. So the accuracy here is given by this formula, so it's true positives plus true negatives over all the negatives. So so here's 100 plus 50 divided by 165, that's 0.91 accuracy. Let's see a bit what we mean by some more accurate measures also, so apart from accuracy. So we have something called, so generally accuracy is very useful when we have x's versus y problems. So for example, if we predict cats versus dogs, but when we cats versus dogs, but the data set was larger, we also had bears, also had lions, and so on. But when we just talk about x versus non-x, like cats versus non-cats, then we can or spam versus non-spam, then we basically have we have these error measures called precision and recall, which basically are more helpful. So again, if we look at the confusion matrix, predicted yeses, nos, actual classes yeses and nos, the precision is defined as true positives divided by all the positives. So true positive divided by true positives plus false positive. That's the definition of precision. And it measures what fraction of the retrieved, for example, like documents or those yeses were actually relevant. So what fraction of the predicted positives were actually positives. And recall is defined as this. So it says true positives divided by true positives plus false negatives. So recall measures what fraction of the relevant records were retrieved. So here again, and accuracy here is defined as true positives plus true negatives divided by positives plus negatives. So and finally, so these are precision and recall are kind of complementary measures. In practice, often we have to make a decision like which one do we prefer? Do we prefer like higher model with something like higher precision or higher recall, and which one, and how do we combine them? So the F measure, and especially the F1 measure, is a way to combine precision and recall. So the formula is basically 2pr over p plus r. This is actually the harmonic mean of the precision and recall. So if you're familiar with harmonic mean, this is basically like arithmetic mean, but a bit differently. So, and essentially, it's a balance between precision and recall. And this is how we can use this F measure, for example, to select what is the best classifier that we want, for example, to select. And it comes from a more generalized measure called the F beta measure, which kind of gives, so this is a particular instantiation when beta equals 1. So for that particular F beta, which I didn't include in the slides, but essentially, you don't have to know that, but essentially it's a more general performance measure, and F1 is basically when we select that beta equals 1. And a beta is basically a coefficient in which you use to weight, I think the precision, if I'm not mistaken. But yeah, you don't have to know the F beta. So here's so let's look back at our example. So we have the table. We can compute the precision, recall, and F1 scores. So we the precision we put in the numbers. So that's 100 over 110. We have 100 true positives here, divided by true positives with false positives. So that's TP plus FP. So that's 100 by 110. So that's 0.91. The recall is true positives divided by true positives plus false negatives. That's 105. So it's 100 divided by 105. That's 0.95. And the F1 score is the harmonic mean between precision and recall. So that's 0.93. Question?
What would be a case where we prefer to use like precision instead of like accuracy, or vice versa?
Accuracy is a mean. It's like a mean of both precision and recall. So precision and recall, you mean? So
You may be okay with a lower recall as long as you've got a really high precision.
so sometimes if your data set, for example, is heavily imbalanced, like for example, you have many of them that are yeses, for example, like actual yeses, for example, versus no's. So you see how the actual yeses are different from actual no's. So you have twice as many, actually almost twice as many actual yeses as no's. So then sometimes that's when you get quite big differences between precision and recall, because precision will weight one of them more than the other. So in that case, it will make quite a difference. Any other questions?
Here in this case, it's an incident that we have two identical numbers, right? Because I think precision
Accuracy and
is
precision.
half
Yeah,
defined.
it's quite it's a coincidence that they won't be the same generally.
Yes, sir.
Yeah.
So precision is how fine-grained is that data that we're kind of analyzing, right?
No, I don't know what you mean by fine-grained. It's more it's given by the formula basically. It's the true positives divided by all the positives basically. It's like the fraction of the positives that were predicted as true. Out of all the positives in the data set, which ones did you predict to be true? Don't worry about it. Honestly, when I first also did this, like it's you don't have to like memorize these formulas like by heart, as long as you know where to search for them and how to where to find them. For example, you can find them on Wikipedia, you can find them on the internet anywhere. That's basically what you need to know. You need to know, you'll have to, for the coursework, you might have to like write them down and implement them, but you don't have to memorize them so by heart. So don't worry about that. Sorry? Let me pick up afterwards because I wanted to finish a few more slides and then like we'll finish. I have one more concept and that's it. So this idea of generalization, how do we measure generalization? We first, what we can do is that we can split a data set into a training set and a test set, and then we train on a training set and then we test on a test set. And this is the idea. So this is the full data set. We split it up into a training set and a test set. And we might also have what we call a validation set. This one is but we'll get to that later. So it's a held out data set. And the idea is that this is how we split. And then the key idea that we do is that instead of doing this just like that, just once, what we can do is that we can repeat the same process, and then we can choose a different chunk of the data set to be the actual test set. So then this is what is called k-fold cross-validation. So in k-fold cross-validation, and this is the last slide, and so don't worry about it, but pay attention. So here, instead of having only one instance of, for example, we choose only one of the parts of this set to be the test set, we iterate over all of these. So then we do the same thing first with the first chunk, then the second chunk, and so on. And then we get, for each of these splits, we get different accuracy measures, or F measures, all those precision recall, and so on. And then we can get different accuracies. And this way we can do estimate much more robust measures of these accuracies. And that's it. Any final questions? No. Okay. So, how does this help in creating k-fold?
Say your training set was really weighted in one direction, you don't have very good.
I'll take it off. Yeah. Yeah, like, do you want to ask Fatemi? She'll help you with that. Yeah, because I think, yeah, she'll help you with that. Yeah, yeah.
I haven't enrolled the course yet because I need a permission code for this course. And
Got it.
I'm a graduate student in BMEB.
In which department?
BMEB, the biomolecular engineering.
Regression, yeah. So I can give you one now if you want. If you write it.
Hey, what's up? Yeah, nice to meet you. Doing this is what? Yeah.
I see there's some chat.
Yeah, we came back right now. I'm not doing these guys. Well, I'm gonna switch to.
I think it was 5 or 6 pages.
Yeah, I had to wait for an regression code for it.
Yeah, so I have one more. 205
205
653.
653.
What's your name?
Jumo, Junmo.
Junno.
Junmo.
NMO. Got it. Got it. Okay. You're welcome. Hi.
This is Orlando. I wrote an email to you, and I have
nice to meet
questions
you. Yeah,
for the
Sorry?
for your last presentation.
Yes.
Yeah, here. And this leave one out. For my understanding, the leave one out means the key should be the one split, right? But I feel a little bit confused. You see here, key equals size of
Size of the corpus. Yeah. So K is in this case is 5. So K is like how many splits you do from the data set.
Yeah.
So so you first do, yeah. It just means how many splits you do. So then so this is k-fold. So basically this is 5-fold cross-validation because you do 5 different splits.
Okay.
And you get 5 different accuracies. For each of these data sets, you get accuracy 1, accuracy 2, and so on.
Yeah. But for me, I think the leave one out is kind of things we can keep one.
Yeah. So leave one out. Sorry, leave one out means that imagine you have the data set is made of 120 different data points. So
Yes.
leave one out means you do it one by one. Literally you leave
Yeah.
one and train the rest. Train on
Yes, that's
119.
my
Then the
point.
second one you train them. Yeah.
So that's why I
Yeah.
feel a little bit confused here.
Yeah.
because,
Maybe I should change the
Okay.
notation and.
This also called auto
Yeah,
band
yeah.
training, right? Because the last one haven't involved with the training, so it could not be. Say you could